Class, welcome back to CSC 143. This is the second of videos in week 9 on binary trees. We're continuing our discussion with common operations on binary trees. Just a quick reminder, CSC 143 is based on the University of Washington curriculum, and I've got the information here on where you can get this textbook. So this video is looking at the common tree operations, how to do the sum, counting the nodes, number of the levels, and the leaves. So I'm actually going to switch into Practice It to show you how to do these common tree operations. Check out my site for how you can use this website, practiceit.cs.washington.edu. You can get a free account and do these problems. I'm going to repurpose exercise 17.3 here. I'm not going to do the problem that is being asked here, depth sum. I'm just going to use this as a test harness to show you how you can calculate the depth. So as with all these tree functions, because of there being a separate tree class from the tree node class, we always have to get the this.overall root and send it to a helper. Now that this helper is where the real work happens, and there's two cases here. We're going to have a base case, and that base case is when if null, and so not having a single node but having just nothing at all. What is the depth of nothing at all? Well, that should be returning 0. And then the recursive case, we have what is the depth? So we have, it's not null, so there's at least one level here. So we have to add 1 for the current level, and then add the recursion of left and right, but not the sum of the left and right, but rather the mathematical max of left and right. So we're going to add 1 for this level, and then whatever is the maximum in the left and the right tree. Now in this case they're the same, but let's assume that we only had the 7 here, and this one is 3. So this would be the max of 1 and 3. So okay, it would be 1 plus 3. So the level, the depth will be 4. Okay, so let's write some code for this now. So this is very simple. If root equals null, return 0. And this is almost equally simple. So we're going to return 1 plus math.max of depth sum left root.left and depth sum of root.right. Only one per in there. Okay, so let's try running this now. Now this isn't going to show that it succeeded because I'm not doing the right problem, but we're going to look at the actual results. Oh, okay, so I just needed a expected. Oh, I do need to close this right there. We're just going to look at the results to see whether it's what we expected or not. Okay, so again, it's perfectly normal this has failed because we are not calculating the depth sum. We are calculating the depth. So 1, 2, 3, 4 levels deep. This is 3 levels deep. See, that's correct. This one is 1, 2, 3, 4 levels deep. That's correct. Here's 1, 2, 3, 4, 5 levels deep. So that's correct. So this works. Now, a lot of students are going to look at this and say, I don't understand. How does that work? Okay, so let's take a look at it. So remember, what is the depth of an empty tree? It's always going to be null. If the tree is not empty, then we're going to add 1 for the current level, and then we're going to recurse. Okay, so that's where this comes from here. Students get confused because it's like, well, where's the work being done? The work is actually being done right here. If that 1 plus wasn't there, then the depth would always be 0. Okay, so that's the simplest, not the simplest, but that's the first example I'm going to give you. How do you do the depth? Okay, so the next thing I'm going to do is I'm going to replace this with actually being the sum. Okay, so we're going to do, what's the sum? So we're still going to have a base case, we're going to have a recursive case. In the base case, when there is nothing, the root is null, it's not a single node again, it's actually the case where there's nothing at all. So there's no value to a tree that has no data. So it's still going to be 0. in the recursive case, we are no longer going to add 1 for the level. We are actually going to add the root.data. And then we are not going to add the max. That would be an interesting one, though. Let's go ahead and do that. This will be interesting. So this will be the max. This will be the max depth sum. So whatever is the maximum path through to the bottom, that's what this is going to be. It's going to be the root data plus the whatever is down there. Let's go ahead and run this and see what this looks like. This should be interesting. Okay, so what is the maximum value path? It's supposedly 23. So that's 9 plus 6 is 15, 19, 21. This one is 9 plus 7, that's 16. That's 19. Nope, but this is 16 plus 18 plus 5 is 23. So that's the maximum path. That's kind of interesting. Hadn't thought about that one. Let's just take one more example here. So here the max path is 26. So I should be able to figure this out ahead of time. It looks like 8 and 9 are going to be bigger. This should be the max path here. 2, 3 plus 6 is 9 plus 9 is 18. 18 plus 8 is 26. So yes, that is the maximum path. So that's interesting, but that's not actually what I set out to do. I was originally just going to do the sum. Okay, so let's just calculate the sum. So it's going to be the root data plus, we have to do value of here plus the value of whatever's in the left plus the value of whatever's in the right. So let's change that to be a plus. Okay, so let's run that, and we have an extra paren. Okay, so let's take a random piece here. This one's easy to add. Okay, so the sum here is 3 plus 5 is 8 plus 2 is 10, 11, 15, 21. And sure enough, that is the output. So we won't go any further testing, but that's the sum. And then the last thing I wanted to do is, oh yeah, I want to do the count. Okay, so what's the count? The count of nodes. So again, it's always, if it's empty, there's no nodes in that. Otherwise, we always have at least 1 for the current node, and then whatever the count is in the left and the right. Let's try running that. So let's pick this example here. There's 1, 2, 3, 4, 5, 6 nodes. Sure enough, 6. And here it's 1, 2, 3, 4, 5, 6, 7, 8. Yep, so that works. And then one thing they mentioned in the book is count leaves. So leaves is just these things out here. This is a leaf, this is a leaf, this is a leaf. So now, am I going to add 1 for this? No. Am I going to add 1 for this? No. Am I going to add 1 for this? Yes. So how do I determine whether I have to add 1? Well, it's because there's no left and right children. So we're going to have to do something unusual and actually check what the left and right children contain. We don't normally have to do that. So again, for the empty case, there's no leaves in an empty tree. So instead, we've got 2 cases here for recursive case. If no children, add 1. And then recurse on left and right. Sorry, if no children, that's right, yes. The other case is if there are children, just recurse on left and right. And actually, we need to add 1 plus the recurse on left and right. We have to add that in. Okay. Let's say the sum. We could actually write this as a single line, but for clarity, I'm going to do it in 2 separate lines. Okay, so we're going to write that code. So if there are no children, which means root.left equals null, and root.right equals null, then we're going to return 1 plus depth sum of root.left plus the depth sum of root.right. Otherwise, we're going to return the exact same thing, except not the 1. And then let's see what we get from that. Okay, and again, this is going to complain, but let's see what it actually did. So we want the number of leaves. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We need to find a different example. Oh, well, here's 1, and then here's 0, and then here's 1, 2, 3, 4, 5, 6, 7, 8. So that all works. So that finishes up 17.3 common tree operations, and come back and watch my next video on binary search trees.